Prior to approval by the FDA, guidewires and catheters undergo scores of testing to verify and validate the device meets regulations. For companies such as 3DT Holdings, LLC, thousands of dollars are spent during the design process by outsourcing testing to third-party companies. However, through partnership with 3DT Holdings and the IUPUI Biomedical Engineering Department, this student design team designed, verified, and partially validated a torqueability measurement system that is inexpensive, adjustable for various guidewires and catheters, simulates anatomical pathways, and supports a predicate equivalency argument. The company can now use the measurement system for in-house prototype testing before sending the prototype to an independent, third-party company for final testing for FDA approval. Now we present the Torqueability Measurement System, otherwise known as the TMS.
The TMS is comprised of 3 systems. The TMS is easily adjustable for multiple pathway diameters and guidewire catheter lengths by using polyurethane tubing, pegboard, and zip ties to simulate cardiovascular pathology. Variance in vascular tortuosity is simulated with pathway configurations, being either straight, curved, or looped. The torqueability test applied to a prototype guidewire or catheter is controlled by a NEMA stepper motor, which is powered and operated by an Arduino Uno, stepper driver, and DC power supply. The stepper motor and guidewire catheter are connected by a 3D printed coupler. As to the torqueability test itself, the stepper motor rotates the guidewire catheter's proximal end 360 degrees in 2 seconds, simulating the approximate speed of a person rotating their hand. The angular rotation of the distal end of the guidewire catheter is measured by the optical measurement system, where an optical flag is inserted onto the distal end of a guidewire catheter. During the torqueability test, a smartphone's camera is used to record video of the optical flag rotating in response to the stepper motor rotation. A white background is used to aid in video analysis. The video is then processed in an ImageJ plugin called OrientationJ, which measures the angular rotation of the flag. The data is then analyzed using Microsoft Excel. When graphing the data, the angular rotation at the proximal and distal ends of the guidewire catheter prototype is displayed to show any lag or whip occurring.
The TMS is designed to make a predicate equivalency argument between a prototype and a commercially available guidewire/catheter for 3DT Holdings before final verification testing through an independent company. For a prototype to pass the predicate equivalency argument, the prototype and the commercially available device should be tested in the 3 pathway configurations, and for 2 of the 3 configurations, the angular rotation for the 2 devices to be within 10% of each other. The prototype can then be sent to a third-party company for final testing. Otherwise, the prototype must undergo design revision.
When developing the TMS, multiple user needs were identified. However, one of the most critical needs to make the predicate equivalency argument was characterizing the sensitivity of the system. If the TMS can detect variances within the system, then it can detect differences between a predicate and commercially available guidewire or catheter. Now, let's take a look at the verification tests. To determine the step rotation accuracy of the stepper motor, angular rotation for the stepper motor coupler component was measured. The angular rotation was measured both manually and with ImageJ. After we conducted a 2-way student t-test, the error of the stepper motor rotation is determined as 2.43%, which is within the 5% specification. Because the distance of the optical flag may affect the torqueability test. To determine the optimal flag distance from the distal end of the guidewire, multiple trials were taken when the flag was placed at 2, 6, 10, and 12 mm away from the distal end. Using the ANCOVA analysis, the 2 mm distance had a p-value greater than 0.05. Therefore, the 2 mm was not significantly different from the ideal 1-to-1 ratio for regression lines. Future tests should implement the 2 mm distance for flag placement. To test the reproducibility of the TMS, 9 trials were conducted in the pathway 3 configuration, and the angular rotation was obtained. When comparing the linear regression lines using the ANCOVA analysis, all trials were significantly different from the ideal 1-to-1 ratio, which has a p-value less than 0.05. This failed to accept the null hypothesis, meaning the TMS failed to reproduce angular rotation results between the trials within the required specification. More tests were required to identify a potential solution to improve the reproducibility of the system.
Looking to the future, the TMS can be characterized further. As previously stated, the TMS has been verified and partially validated. However, due to the external circumstances, the testing has only been for guide wires. First, validation for guide wires needs to be completed. Then, the system needs to undergo the same testing protocols with catheters. To increase the accuracy of the system, more trials are needed for the verification tests, i.e., increase the sampling size of the tests, and more verification tests for the individual TMS components to further characterize and optimize the component's performance. We would like to thank several people for helping our student design team develop our 2020 Senior Design Project. We are so grateful to the IUPUI Biomedical Engineering Department, Professors Miller, Smith, Wallace, and Yoshida, Sherry Clemens, and our sponsor William Combs of 3DT Holdings LLC for guiding us in developing the TMS for guide wires and catheters.
Thank you for watching.